In this fifth part of the course, we will focus on additive technologies that come into consideration for the production of die-casting dies. Additive technology brings new possibilities to the production of die-casting dies. However, because it is a completely new, rapidly developing technology, there is a lack of support in process design, similar to that provided by Nadca 207 for classically manufactured steel materials. Therefore, we will try to clarify some of the problems and explain the content of the newly published Nadca 550 document, entitled Tooling Certification for Die-Casting Die Components Fabricated by Additive Manufacturing. Before we start with this interactive course, please enter your full name and surname in the field below and press OK. This name will then be stated on the certificate of completion of the course together with the test results. Although additive technologies represent modern and progressive methods of manufacturing metal parts, it must be said that Nadca 207 does not yet know these technologies. The word "doesn't know" should be understood in the sense that it has not been verified that 3D printed parts have identical properties to parts produced by conventional methods, and it is therefore not entirely clear what their resistance to thermal fatigue will be. It is also not yet resolved if the powder materials for 3D printing are identical to those classically produced and recommended, or if they will be recommended completely differently. The problem must also be seen with standardization. Therefore, in order for AM technologies to have the same definition as classic ones, there must be standards for terminology, parts design, powders, for printers qualification, for printing processes, for all post-processes, including hot isostatic pressing technology, or for testing or operators qualification. Only when all this is done, additive technologies can appear in the Nadca 207 specification. But it takes time. The first step is the document published by Nadca under number 550. It already partly answers our questions about 3D printing, but still in a general way. However, it does not address the lifespan of the mold parts produced in this way at all, and is therefore only a basic document, which must be followed up with more detailed specifications in the future. Therefore, it is necessary to accept the fact that the use of inserts from 3D printing technology has a legal pitfall in that it must be approved by the tool owner or the die-casting foundry, which will use the tool with an emphasis on economy and with awareness of all possible risks. Even before we start in this course with the description of individual technologies and operations, we should ask ourselves what our expectations and our doubts are. How should we actually prepare drawing and technological documentation for individual parts of the die-casting die? How to actually draw the shape of such a part, and how to place it on the printing platform so that the resulting shape corresponds to our ideas and does not have defects that would prevent its further use? How to ensure that after printing we get a net shape, or if that is not possible, a near net shape? Which powder steel should we choose for our part in the die-casting dies? Is it 1.2709, H13, Ampo W360, Heatvar, Davar, or other? Which ones are Nadca approved? If we already choose powder steel, is it described what the quality of this powder should be? What should be the size of the grains, their shape, the statistical distribution, or what is the prescription for the repeated use of the powder? Are there any Nadca recommendations? If we print a part from the selected powder steel, is the permissible porosity of the parts defined after 3D printing? And is it even economically possible to print parts with minimal porosity? Is there any Nadca regulation or recommendation for printing parameters? Is a heated printing platform required for all types of martensitic steels? And if so, at what temperature? As in heat processing, the vacuum furnace must be in a validated state, according to AMS 2750. Is there any regulation that says how to validate the printers so that the results are reproducible? If we already print the part, is there a prescription for heat treatment and all other post-operations to maximize resistance to thermal fatigue? Under what conditions can hot isostatic pressing be omitted? And under what conditions must we apply it? Is there any regulation on how to test the print result? It can be assumed that we will need to perform reference toughness tests on each printing platform to verify the printing process. Do we have information on how to place these samples on the platform and in which direction, so that they best represent the state after printing? We will try to answer all these questions on the next slides. What do we actually imagine when we think of additive technologies? These are new, modern production processes based on powder technologies. Their benefit is completely new possibilities for the production of shaped inserts. On the other hand, this novelty is an obstacle because they are not sufficiently verified, and therefore they are only slowly getting into norms and standards. The development of the Nadca 207 specification shows how long and complicated the path was to create a generally recognized standard for achieving maximum resistance to thermal fatigue for classic wrought steels. It is therefore a long way off, and the full integration of AM technologies into production processes will take some time. However, not all of these additive technologies are suitable for die casting molds. Therefore, all those that use binders, such as the binder jet method, MIM, metal injection molding, can be excluded. In the following, we will therefore only deal with technologies that work only and exclusively with the application and melting of metal powder without a binder. With AM technologies, the part is created on a 3D printer by gradually applying layer by layer. What takes weeks, sometimes even months, with AM technologies can be achieved in days and with a single clamping. However, AM technologies also have their pitfalls, and therefore they must be considered as complementary technologies to classic ones for the time being. They allow us to change the economics of die production, or the production parameters of the tool at the users, for example, thanks to better flexibility in creating a cooling system, or a more complex shape simplifying the production process and improving product quality. On the contrary, even with the greatest effort, printed materials still do not reach 100% density, and therefore not even the mechanical properties corresponding to materials produced by the classical metallurgical process. On the screen are examples of 3D printed parts. These are parts of die casting dies or plastic injection molding, where the advantage of 3D printing in creating a cooling system is significantly applied. Cooling channels designed in this way cannot be manufactured using conventional methods. If we are going to talk about AM technologies according to Nadca, publication number 550, then we have to focus only on those that are applicable to die casting dies. There are two basic ways. The first is a method called direct energy deposition or direct metal deposition. This is a method where a layer of metal is applied from additional powder or wire by fusing with a laser or an electron beam. This method can be advantageously used for repairs and renovations of die casting inserts, or for surface modification, but only exceptionally for the prototyping. Considering the way the process is conducted, there is no significant dimensional limitation on size. For example, this device for DMD technology is a portal version with a table size of 1000 by 600 millimeters. The entire range of powder materials can be successfully applied, from powder steel type H13 through maraging steel 1.2709. various stainless steels to superalloys based on titanium, chrome, or nickel. However, it is necessary to take into account that, even in this case, printing must be followed by some heat treatment procedures, especially annealing to remove stress. This is also why access to the same size equipment for heat treatment must be ensured. The method is not suitable for the production of large compact inserts due to the high investment costs and the size of the equipment. Printing time combined with high depreciation will create a significant economic barrier. A new progressive solution to this technology is also a series of machine tools from the DMG Mori company. For example, the LaserTech 125 DED Hybrid, where the application of powder materials by the DED method and the subsequent machining of dies are combined in a completely unique way. The second method, according to the Nadca 550 publication, is the powder bed fusion method. It is a 3D printing process where the printed product is created layer by layer by gradually fusing the powder. Two basic methods are currently used. The electro-beam melting method, when the melting source is an electron beam, and the selective laser melting method, when a laser beam is used to melt the powder. In the first case, the layer is formed in a device with a high vacuum, because this vacuum is a condition for the existence of an electron beam. In the second case, the layer is applied under atmospheric pressure of a neutral gas, such as nitrogen or argon. However, the laser beam and electron beam methods are so different that they are not interchangeable, and this needs to be taken into account when manufacturing die casting dies. Equipment representatives for the laser bed fusion method are equipment from EOC, Renishaw, or SLM solutions, while for the electron beam method, they are equipment from Arcam. For clarification, it is still necessary to say that the name SLM is the trademark of the technology of the company SLM Solutions, and the abbreviation DMLS is the trademark of the company EOC. Today, the most widespread printing method is the powder bed fusion with laser beam. This type of printer allows you to print all metals as alloys of copper, aluminum, titanium, various types of steel. The process takes place under atmospheric pressure of nitrogen or argon, depending on the type of material. Due to the intensity of melting, gaseous nitrogen can be partially split into atoms, and it can then bind to the molten metal in the form of nitrides of alloying elements, such as chromium, molybdenum, vanadium, titanium, and others. Therefore, for highly alloyed materials with nitride-forming alloy elements, it is necessary to use neutral argon gas. This also applies to material H13 or 1.2709. The quality of the print is affected by the laser power, scanning speed, raster size, the way individual traces are overlapped, and the fusing angle and many others. The actual product is printed on a metal platform that can be preheated to 200 to 500 Celsius, but the powder melts when cold. Due to this method of printing, the product is subjected to high stresses, and within 24 hours after printing, it should be subjected to annealing to remove the stresses. If an air-hardenable material such as H13 powder steel is being printed, then this problem is even more pronounced due to the martensitic transformation taking place. The advantage of this method is its availability, and above all, the fact that the powder enclosed in the cooling channels is easy to extract after printing. This property enables printing of special inserts with cooling channels, unproducible by classical methods. The disadvantage is the printing speed. Pictured is a spare part made of 1.2709 material weighing 89 kilograms, which was printed on a printer with 4 lasers for 17 days. This method cannot print a product with 100% density. The maximum achievable density is then tied to the economy of printing. If we want to apply this printing method, then the production process consists of the following operations. Pre-operations, actual printing, annealing to remove stress, separation of the product from the base plate. If we want 100% density, then hot isostatic pressing, heat treatment for H13 material hardening and at least 2 tempering cycles, cleaning and surface treatment, product inspection and completion. The condition for applying the powder bed fusion method is therefore not only a printer, but an stress annealing furnace with temperature range according to the printed material, or access to hot isostatic pressing technology and vacuum heat treatment. In the following video, you can see how the printing method looks in practice. The source of the video is promotional materials from EOC Company. The second printing technology, the electron beam melting, has some advantages over method with laser beam. Above all, it is possible to print at high temperatures, even over 1000 Celsius, and thus without significant internal stresses. There is therefore no risk of the product having cracks, as is the case with the laser method. The electron beam has significantly higher performance and scanning speed. The print surface is first preheated by the electron beam, then the contours are created, following by hatch melting. Because the beam has a high speed, it can simultaneously print several products at once. As in the previous case, the print quality is tied to a number of process parameters. Their setting is then part of the know-how of the one who prints the products. The disadvantage of this type of printing is that it is not possible to print easily vaporizable metals such as zinc, magnesium, lead, or copper, and alloys of these elements. But the big advantage is that it does not need a platform for printing, and the parts are printed in space in a powder bed. Therefore, the volume of the chamber can be better used for printing efficiency. A big disadvantage is that due to the high energy of the beam, the area around the printed product is also affected, and it is therefore not easy to extract the powder from narrow or blind cavities. This is a major weakness of die casting dies, and therefore this type of printing on die casting inserts will only be used exceptionally. The production procedure will be similar to the previous case, but it will not be necessary to apply the annealing operation to remove stress and separate the product from the platform. So these are the following steps: pre-operations, printing, removal of products from the powder bed, and cleaning from the powder. If we want 100% density, then hot isostatic pressing must follow. Heat treatment in the case of H13 steel, hardening, and at least 2 tempering cycles, surface cleaning and machining, product inspection, and product completion. This video will show you electron beam printing method. It is a presentation material from Arkham.
Additive manufacturing offers greater freedom in design and allows for the creation of optimized parts that are not constrained by the limits of traditional manufacturing. Arkham EBM has the unique ability to tightly stack parts within the build in order to increase productivity. An optimized build file is sliced and loaded into the Arkham EBM system. Following this, metal powder is loaded into the machine. The build chamber is then closed and a vacuum is created to ensure a clean, controlled environment that allows for the processing of reactive material. Next, Arkham EBM's powder layering system evenly distributes a thin layer of powder on the build area. A powerful 6 kilowatt electron beam heats the powder bed to the optimal ambient temperature and then proceeds to melt the powder. First contour melting and then hatch melting. The electron beam unit generating the beam contains no moving parts, allowing for extremely fast and accurate beam control. The build environment is kept hot, reaching temperatures exceeding 1000 degrees Celsius, resulting in no residual stresses and allowing for the processing of cracked.
The beginning of every design for 3D printing is digitization. We draw what we wish to produce in a 3D graphics system. Today, the most commonly used professional systems are AutoCAD, SolidWorks, CATIA, but free programs such as FreeCAD and many others are also considered. What is important is that the drawing must be converted into a polygonal structure corresponding to the scanning motion of the laser or electron beam. A so-called STL file containing instructions for the 3D printer is created. This file represents the transformation of our idea into data for 3D printing. The density of the polygon mesh for printing is adjustable, and the printing time will correspond to this density. The material density or porosity will also correspond to the printing strategy, as well as the mechanical properties or, as a result, the material's resistance to thermal fatigue. The printing strategy is also very important for the result. As you can see, it can be one-way, two-way, or so-called zigzag, in the case that the beam melts the material alternately there and back. Part of the printing strategy is the multiplicity of remelting, where one spot of the surface can melt once, twice, or even 3 times. This will, of course, be reflected in the porosity of the material and the number of defects after printing. As part of the printing strategy, the target density requirement is also set. As can be seen from the figure, with a layer thickness of 40 micrometer, a beam speed of 500 micrometer per second, and a laser power of 100 watts, a density of 98% can be achieved if the distance between individual traces is up to 50 micrometer. If we increase this distance to, for example, 200 micrometers in order to save time, then the achieved density of the material will be only 89%. As a very important parameter for hot work steels of type H13, as well as for other carbon steels with martensitic transformation, is the temperature of the substrate plate. This has a significant effect not only on the internal stress, but also on the resulting density and structure. One of the reasons is that if we print at a temperature above the martensite start, one of the problems is reduced, which is the martensitic transformation in the initial stages of printing. It has been verified that if the platform temperature is 400 to 500 Celsius, then the applicability of this technology for hot work steels will be significantly improved. Even if it is only a preheating of the platform for the initial layers of printing, it must be remembered that other subsequent layers are heated from the melting process, and when the printed product is gradually immersed in the powder bed, the body of the printed insert will maintain a high temperature in the powder. Heating to 500 Celsius significantly reduces the stress in the printed product and at the same time reduces the effort to bend. On the left of the picture is the prediction of internal stresses in a body made of titanium alloy Ti6Al4V material at a substrate plate temperature of 500 Celsius, on the right side at 200 Celsius. Internal stresses are significantly lower. It is the same with deformations. On the left is the deflection of the sample on a substrate plate at a temperature of 500 Celsius, on the right at a temperature of 200. The result at a higher temperature is by 95% better than when printed on a platform at a temperature of up to 200 Celsius. In the last picture, you can see the cracks inside the part from of H11 material, printed at a temperature of 200 degrees Celsius, image on the right, and the state after printing with a heated substrate plate at 500. The difference is quite obvious. The high temperature of the platform reduces the stress in the printed product, and thus also the tendency to form internal cracks. The strategy of the printing will fundamentally influence its economy. If we were to try to print a cube with a side of 200 millimeters and a weight of approximately 63 kilograms, with a thickness of individual layers of 100 microns, the distance between the tracks also 100 microns, then the printing time would be 18.5 days. At an estimated hourly rate of the printer of 100 euros per hour, the price of printing would be 44,000 euros. The print density will be somewhere around 98%. We don't know if it's acceptable quality, but it's definitely an unacceptable price. If we increase the grid to 200 micrometers, then the price will drop by half. But at the same time, the porosity of the material will increase to 89%. But this is already a value that does not guarantee us high-quality mechanical properties. That's why we have to start thinking about hot isostatic pressing technology. Even if we have a porosity of 89%, after applying hot isostatic pressing, we will achieve a density of 100%. However, the cost of HIP will only be up to 1,000 euro, and means a saving of almost 20,000. It is a question of what criteria to set for the use of HIP technology, when yes and when not. We do not know the relationship between the toughness of the material, resistance to thermal fatigue, and porosity. But since porosity represents random defects that we cannot recognize from a macroscopic point of view, hot isostatic pressing significantly increases our certainty that these random defects will be removed. At the same time, it allows us to print with significantly density, which means cheaper. Therefore, if printed parts are to have the same service life as parts made of forged material, hot isostatic pressing technology should always be used. I have already mentioned the example of printing a moving part of a die made of powder miraging steel 1.2709, weighing 89 kilograms on an EOCM 400 printer with 4 lasers. The printing time, even though it was done on the most modern and powerful printer, took 17 days. And what was the economic result? When all the costs and all the benefits were added up, the overall result of the project was a loss of -40% compared to the state when this part was manufactured in the classic way. The life of the part decreased by 20%, and the repair costs in both. The tool shop and foundry increased by 50 and 60% respectively. What does this imply? 3D printing may therefore not be a real economic advantage. And if it is to be, we must look for ways to accentuate these advantages. And since the cost of powder steel and printing is the main item, then we have to solve the printing cost with a suitable printing strategy in combination with the maximum values of thermal fatigue resistance. What exactly is HIP technology? It is a technology called hot isostatic pressing, and its meaning is that at close to the material's melting temperature and at high pressure of up to 2,000 bars of argon, it suppresses most of the porosity inside the material. This is also very important for die casting dies. If a printed part is to have the same thermal fatigue life as a compact, classically produced material, it must also have 100% density or be close to it. But there is one more aspect, that is the reliability of the result. The pores in the printed product are randomly distributed. They may or may not be there. But this cannot be recognized from a macroscopic point of view only by destroying the part and its metallographic evaluation. This is, for example, the problem of blades for aircraft engines, produced by the investment casting method. Precisely because there is no certainty of not porous state, the hot isostatic pressing operation is mandatory on every piece. The same principle must therefore also be applied to die casting dies if we want to maximize service life. The only problem is that hot isostatic pressing production capacity is not always available, so the problem is circumvented by trying to optimize printing so that HIP does not have to be applied. This means choosing a printing strategy so that the density of the material after printing is as close as possible to 100%. But economic reasons clearly speak in favor of HIP technology. If we accept the current situation where HIP is not available, and at the same time, the printers only have a heated platform up to 200 Celsius, then we have to put up with high internal stresses in the printed product. This applies both to miraging steel 1.2709 and especially to carbon steels with martensitic transformation of the type 13, Dievar, EMPO W360, and others. Examples are in the picture. The disadvantage of internal tensions is that they are not tangible, and we only find out their presence at the moment when a crack occurs. In order to avoid this, it is necessary to include stress relief annealing as quickly as possible, within 24 hours at the latest. This stress relieving is done before the printed part is separated from the printing platform. Stress relief annealing is the process without recrystallization, below temperature A1. The range from 600 to 650 Celsius is usually used, but it depends on the material from which the product is printed. Since annealing takes place at temperatures where oxygen diffusion can already play a significant role, it is necessary to anneal in a protective atmosphere or, even better, in a vacuum furnace. This is the only way to prevent oxidation along the grain boundaries, which can worsen the impact strength of the material. Stress annealing without a protective atmosphere is not recommended. Now we are getting to our own materials, which can be used for 3D printing of parts for die casting. The most common is miraging steel 1.2709, also known as M300. Böhler sells it under the trade name AMPOW722. It is a steel with almost no carbon, so there will be no problem with martensitic transformation. This is also the reason why printing with a platform temperature below 200 Celsius can also be considered. The internal stresses will be lower than if we were to print from steel type H13 or other carbon steel of a similar type. Steel is also specific in that it does not require heat treatment at high temperatures. Annealing to relieve stress is replaced by precipitation, hardening, or aging. At temperatures of 490 to 540 Celsius, the hardness of the material increases due to the precipitation of intermetallic phases. The holding time is normally applied from 2 to 8 hours, but the time does not have as significant effect on precipitation processes as temperature. Importantly, in addition to the precipitation of intermetallic phases, this process also releases stress from the print. How the mechanical properties of steel change can be seen in the following diagrams from tensile tests after printing, after aging for 1 hour at a temperature of 540, and after aging 8 hours on the same temperature. The precipitation hardening process reduces the tensile strength, increases the yield strength, and increases the ductility of the steel. Although the use of this steel for die casting dies means a simplification of the printing process and subsequent thermal operations, the main disadvantage of this material is that it does not achieve the resistance to thermal fatigue that we know of forged materials. This can be seen in the presentation from the Böhler Company, where the ratio between the thermal fatigue resistance of the material 1.2709, both classically manufactured and used for 3D printing, is shown. All this in comparison to material H13. Although this is a commercial presentation, the value of 30% for use on die casting molds is not very optimistic. So this steel can only be recommended for rapid manufacturing of spare parts, for die repairs, for prototyping, but not for OEM parts. And if so, we must already take into account this predicted life when designing the die and produce 2 or 3 pieces instead of 1 insert, so as to ensure the target life of the die-casting die will be reached. If we were to believe that Nadca 207 recommends the right materials, then we should focus on available powders from this category of steels for die-casting dies. This is primarily the H13 material, when powders can be purchased, for example, from the Oerlikon Company. The Böhler Company launched a powder under the name AMPO W360, which corresponds to steel type 1.2367 in its composition. And last but not least, the Uddeholm Company started offering Divar steel powder. It is just a question of which printing strategy to choose so that the thermal fatigue resistance is at the level of classically produced steels. What is unclear is the temperature of the heated substrate plate, when a large part of the literature shows that a temperature above 400 Celsius significantly increases the success of printing. And further, it is the use of HYP technology to eliminate random defects or to improve the economy of printing when printing with a thickness layer above 40 microns. This image shows the datasheet from Böhler Company for MPOW 360 powder. It is the first commercially published data for impact strength values on 3D printed parts. If we compare these values of 8 to 14 joule with the Nadca 207 values for the same type of steel, then these values are equivalent to the Nadca 207 recommendations. So the average value is 13.6 joule. The minimum is 10.8 for the test of steel capability. It means after hardening in oil. However, since we do not examine input properties in 3D printing, but print finished parts directly, the values of 10.8 and 8.1 joules after hardening for classically produced steel are worse than the values reported for powder steel. That is very optimistic. However, the Böhler Company does not publish the printing parameters, nor if it has applied hot isostatic pressing technology, so it is up to the user to verify and confirm the printing parameters themselves. For verification, however, it must not be forgotten that samples for impact tests must be printed at the same time as the insert itself. But it is also necessary to remember whether the samples will be in the plane of the platform, or perpendicular to it, or at an angle of 45 degrees. In all cases, the result will be affected by this very fact, as well as the subsequent hardening and tempering, which must certainly be implemented. In the case of printing material H13 AMPO W360, DIVAR or HEATVAR, the following procedures are possible. The first process flow involves only printing and stress relief annealing. The printed part is used without quenching and tempering, with a structure corresponding to the annealing process. The part properties are depending on the powder quality, printer, printing parameters, printing strategy, platform temperature, and many other parameters, and it can be assumed that the structure will contain a high amount of only once-tempered martensite and a large portion of residual austenite, with very negative properties to meet the thermal fatigue resistance requirement. The second process flow already applies vacuum heat treatment. Since there are no known verified recommendations for quenching and tempering, probably the least evil is to apply the same heat treatment procedure as for the compact material according to Nadca 207. This process flow changes the brittle structure after 3D printing to a tough structure with double or triple tempered martensite, with some residual austenite. The only problem will be how the porosity of the print affects the thermal fatigue resistance. The third process flow already includes HIP. This will ensure that the structure will be non-porous and 100% dense after printing. It should be noted here that HIP does not and cannot solve surface defects. With Quintus devices, it is then possible to perform all operations at once, that is, both annealing to remove stress and HIP, as well as subsequent hardening and tempering. Whether such a process is economical is up for consideration. In any case, Whether this process is carried out in one or more furnaces, it is the only way to maximize the mechanical properties, and thus thermal fatigue resistance of the 3D printed die casting dies. All thermal processes should preferably take place in a vacuum or under a protective atmosphere. 3D printing must therefore also include access to these technologies and the corresponding furnaces. If we really want to maximize the useful properties, we cannot risk losing part of them by using an unsuitable device for the given thermal operation. Now let's do a recapitulation. Additive technology for the production of die-casting dies can be applied if it is agreed between the tool supplier and the user. Nadca is still validating this technology, and parts made with AM process are not guaranteed to have the same lifespan as parts produced by classic technology. For the manufacturing of die-casting dies, the powder bed fusion with laser melting method is preferred over electrobeam technology. The direct metal deposition method can be used to repair inserts and restore their shape, where the additional material is powder or wire, and the source is a laser, electron beam, or arc discharge. The most widespread material for 3D printing is precipitation hardenable powder steel 1.2709. The advantage of this material is that it is less prone to cracks, is not burdened by transformation stresses, does not require a high platform temperature, and heat treatment is also easier. However, its resistance to thermal fatigue is significantly lower than that of the material like H11, H13, Diavar, Hiatvar, or Ampo W360. OEM parts should be printed from powder steels with martensitic transformation. These prints require a high platform temperature, at least above the martensite start line. Annealing for stress relief must be included within 24 hours at latest. Subsequent heat treatment. Hot isostatic pressing or quenching and tempering is no longer time-limited. If there is a reason for 3D printing, for example more efficient cooling of the insert, the economic parameters of printing need to be taken into account. Hot isostatic pressing technology can bring significant savings. Nor did the Nadca publication number 550 provide binding rules for the printing of die-casting mold parts. That is still the future. What to say in conclusion? Classical steelmaking process has evolved over centuries, and only recently, with the development of new remelting methods, we have reached today's top level. However, AM production will have the same timeline. Everything is just beginning. Manufacturing and assortment of powdered steels, technical level of printers, printing parameters, post-processes. The estimated roadmap for AM technologies is for at least the next 10 years. This is also why Nadca 550 does not draw any conclusions, and the only absolutely essential recommendation is to collect data, evaluate it, and adapt the subsequent process with regard to our previous results. In conclusion, I will provide some results from our research activities. Since wrought Diavar steel has shown excellent results in the long term, we have also invested in this steel in powder form. Regarding the technological process, we believe that reliable results cannot be achieved without hot isostatic pressing technology. Even if we ignore the economics of printing, we cannot stabilize the results of 3D printing without eliminating hidden defects. It is the same as with parts for the aerospace industry. Aircraft engine blade castings, as well as other parts produced by the investment casting method, are strictly subject to the hot isostatic pressing process. The reason is not that it is impossible to cast parts without defects, but that despite all efforts, there may have hidden defects in the casting that need to be eliminated. The same applies to 3D printing. The reasons for internal defects in 3D printed parts are obvious, and our analytical methods are not sufficient to completely detect and eliminate them. And if you're not convinced, even though we have a print density of 99.97%, the material still contains millions of submicron pores. Our process therefore consists of 3D printing, hot isostatic pressing, and subsequent heat treatment in vacuum furnaces. So far, we have tested samples for impact tests according to Nadca 207. To simulate the hardening of real die inserts, the test coupons are placed between two plates, each weighing approximately 13 kilograms. The entire process is controlled by thermocouples TS and TC, as shown in the figure. After hardening, 3 tempering cycles follow. The figure shows typical fine-grained structures. The most interesting thing is that after quenching, we do not have a fully martensitic structure, but a structure in which there are more than 34% carbides and approximately 5% of retained austenite. This structure changes after the first tempering, and only now do we detect a structure with tempered martensite, without carbides and near zero retained austenite. As for the impact tests, we achieve values higher than for Devar wrought steel. As for hardness, these can be seen here in this graph. The material behaves almost standardly. Only after the third tempering the hardness decreases faster than we thought. And as for the residual austenite, even if it is detected after hardening, immediately after the first tempering, we see that it has completely transformed into martensite. Overall, it looks very promising. However, we are just starting with real pieces. So we will see. The development continues. There are still many things to be clarified. In any case, we can already say today that the material from 3D printing behaves differently than the classic forged material, and we have to deal with that. The production processes of such inserts for dies for high-pressure casting will therefore differ from those we use for classic production according to Nadca 207. We are just before testing, and at the moment, it is difficult to say what the service life of such an insert will be. But we still hope that our path is logical, and that using hot isostatic pressing, we will prepare the die material in top quality and without potential defects in the structure. And if you want to try it too, don't forget to print impact test samples with each platform. These must go through the entire process, just like the die insert. Only when these impact tests are performed can we say that we have met all the necessary process parameters and properties for thermal fatigue. Additionally, we have proof that we are reaching values just required by Nadca 207. The course of additive technologies for die casting dies is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a permanent license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0 on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system LMS that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.